Hi everybody. Okay, so some of you had to do dual enrollment today, so you had to leave class, and I essentially covered all of 2.1 and a little bit of 2.2, and I promised that I would make a video to cover that. As I said in the beginning of class, we don't have our books yet, so I'm going back to the book by George Best. The calculus is the calculus regardless of who writes it, so the concepts are going to be the same. Okay, and section 2. All of chapter 2 I actually posted a PDF on Edsby, so that way you have that part of the book so you can read over it if you like. And let's just have a look at this. Okay, so section 2.1 starts with the derivative function. So where I begin with is where Best begins with, which is average and instantaneous velocity. So the first thing we established in class is that the average velocity is given by the distance traveled over time. Okay, so make sure you know this formula. It's average velocity. And essentially, if you're looking at it from a graphical perspective, so let me get a little bit closer to this graph. If you're looking at it from a graphical perspective, what we can say is that the average velocity of a function is equal to the slope of a tangent line. Okay, so I've got some colored markers here that I'm going to be using, but the idea is this. So I'm just talking graphically now, not anything else. Okay, in AP Calculus, you're going to have a lot of graphs that you're going to have to interpret and maybe find the average or even instantaneous velocity of it. This is of a car trip over a 2-hour time span. So if you were asked, what is the average velocity of the entire trip? To find the average velocity given a graph, all you have to do is connect the endpoints of the graph with a line. Okay? Now this blue line that I just drew in my book, it's okay because it's my book, I actually paid for this book, is called a secant line. So this is a secant line, and a secant line is just a line you learned in geometry that intersects a graph at 2 or more places. Okay, but we're just going to focus on 2 points of intersection. And this is beautiful because we know how to find the slope of a line, right? We know that the slope of a line is equal to y2 minus y1 over x2 minus x1. So that's just the change of y over the change in x. Oops. Okay, so if I know this point, and I do, it's 0, 0, and I know this point, which is 290, I can take the y's, 90 minus 0. By the way, we denote the slope of the secant sign as m sub sec, and I write small, so you may not notice it there, but on a regular piece of paper I'd write it as m sub sec, meaning the slope of the secant line. Okay, well, this is the same formula. The slope of this line is the slope of any line, so it's y sub 2, which is 90, minus y sub 1, which is 0, over 2 minus 0, the change in x. And 90 divided by 2 is 45. So we could say that the average velocity of this trip, for this 2-hour trip, was 45 miles an hour. Now, you might be asked, well, what was your average velocity over the first hour of the trip? Well, the first hour starts at 0 and ends at time is equal to 1. This is the first hour. So I would be finding the slope of that secant line. Well, this is the point 140. So all I have to do is repeat the process, right? The slope of the green secant line is 40 minus 0 over 1 minus 0, or about 40 miles per hour. If I wanted to find the slope of the secant line over the second half of the trip, well, that would go from the point 140 to the point 290. So it would be that secant line. And the slope of that secant line is equal to 90 minus 40 over 2 minus 1, which is just 50 miles per hour. So the idea is, depending on the interval of time that you're looking at, your velocity is going to change, because every point along that original curve has a change in velocity. There's a rate of change for every point. Okay? I could have chosen this tiny little interval here from 0 to a quarter, and figured out what the point was, well, what this point is here, the x and y coordinate, and use that if I wanted to, and on and on and on. So we can do all kinds of things. The interesting thing comes from when you're asked to find the instantaneous velocity. Okay, so the slope of a secant line over an interval is just the slope of a line between two endpoints over some interval. Could be any one that you're asked to find, and on this graph we could find a whole bunch. The problem happens when we say, I want to know what your velocity was at exactly the moment when t is equal to 1.5 hours. Not between 1 and 2, or not between 1 and 1.5, but exactly at the moment when time was 1.5 hours. Well, the problem is now I only have a point. And if I draw a line through that point, the problem is I don't have a second point, so I can't use this formula. So I have to decide, how am I going to find that out? What am I going to do to help me figure this out? Because right now, there's no way, I have no way of knowing. I have no way of doing this. I've never been taught this. So what we're going to do is what we call secant line approximation. So let me see if I have another graph on the next page. Oh, good. Since I colored in my graph. So here's the same graph, and at this point here in the example, they are finding the average velocity over the second half of the trip. So let me change this and just say, I want to know what is the velocity at the instant, so the instantaneous velocity at the moment when t is equal to 1. Well, I know that this is the point 140, because we established that on the other page. But I have no other point that this little tangent line goes through, so I don't know what to do. Well, we found the average velocity from 0 to 1, which was 40, I believe. And we found the average velocity from 1 to 2, which was 50, I believe. Let me just check. Yeah. The slope of this secant line here was 40. The slope of this secant line turns out to be 50. So the idea is this. What I'm going to do is I'm going to take the average of the slope of the secant line on the left of that point and the slope of the secant line on the right, and that's going to give me a pretty good approximation of the slope of the tangent line. So all I have to do is say, the slope of this tangent line is approximately equal to, because I'm estimating, 40 plus 50 divided by 2, which is 90 halves or 45. And we said originally that the average velocity over the entire trip was 45 miles an hour. So at this moment in time, our velocity was 45. Okay, so the average velocity over any interval is just the slope of the line joining the endpoints in the interval, and that line is called the secant line. Okay? If we want the instantaneous velocity, we have to do something a little bit different. So let's have a look back at the secant line problem. So I'm on page 85 right now. And let me just see, yeah, I have a pencil. I'd rather use a pencil. Okay, so this is some function f in the plane. And there's a point A on this function here, and there's a point B. And so if I wanted to figure out the average rate of change, same as average velocity, okay, velocity is a rate of change. So if I want to figure out maybe what the average velocity or the average rate of change is over this interval from A to B, I could do it, because I can construct a secant line and I know how to find the slope of a line. Bear with me. They're calling, so instead of calling this, 1, 2, 3, 4, they're letting this first thing be A here. So if x is equal to A, then this point is A, comma, f of A. Is that okay? This function is some function f of x. So if I plug in A into the function, I get the function evaluated at A out. So this is my x coordinate, this is my y coordinate. On this side, I've got this B here. But what I want you to realize is that we're going to move over from A, this teeny tiny little amount in the horizontal distance, thus the h here. Okay, so we're going to move over this tiny, tiny, tiny little amount. So if I add A plus some horizontal distance h, then the x coordinate here becomes A plus h. So the point has coordinates A plus h, comma, f of A plus h. Is that okay? Again, this is the x coordinate of point B, this is the y coordinate of point B. This is just a more sophisticated way of writing it. The vertical distance between this point and the x-axis is just f of A plus h minus f of A, right? This distance minus that distance. And the change in the x's is A plus h, well, this point here, this value, minus A, which leaves us with just h. Okay? So, using this notation, the average velocity, the slope of the secant line, these are equal, m sub sec equals the average velocity, which is the same as distance over time, can be written as such: f of A plus h minus f of A, that's the change in y, over A plus h minus A, which reduces to just h, change in x. This is nothing more than the slope of a line. Okay? Average velocity or average rate of change. However, whatever the context is for the problem, we think of it, it's all the same. And rather than saying, so let me get a piece of paper here. So perhaps, you have some curve, and we'll call this 1 and we'll call this 4. Okay? Let's call this function x squared. It's part of x squared. It's a really sad looking part of x squared, but anyway. If I plug a 1 in to this function, I know that f of 1 squared is equal to 1, right? So this would be the point 1, 1. And if I plug a 4 in, f of 4 is equal to 4 squared, which is 16. So this over here would be the point 4, comma 16. You with me on that? Now if I wanted to find the slope of the secant line, I would say 16 minus 1 over 4 minus 1, which is 15/3 or 5. Right? The only difference between this and this is that this is in notation form. Okay? And the other thing is that these points here, they look really far away from each other, but you have to imagine that that's zoomed in, and on that curve, A and B are like that close to each other. So it's zoomed in and we're looking at this little tiny distance in between them. And that little tiny distance in between them is called h. Alright? Now, let's suppose I draw a tangent line at point A. So, tangent to the curve, so like that, roughly. Okay? And I want to know what is the instantaneous rate of change, or the instantaneous velocity, or just the velocity, they all mean the same thing, when x is equal to A. Well, I can use the secant line, because here's 2 points. I can use it to approximate it, but this slope is, say, a 1, and this is almost a 0. So it's a really bad approximation, although it's one way of doing it. I could instead of moving over this far, a plus h, I could maybe move over from here to here and call this a plus h and find the slope of this secant line. And if I did that, it wouldn't be as bad as this approximation, because this slope is certainly not as steep as this one, and it would be a little bit closer to the slope of the tangent line, but it would still be a rough estimate, because, and probably not a very good one, because the slopes are very different, right? So the idea is, maybe my a plus h will be here. I'm not going to move over quite as far. My point's going to be here, and I'm going to attach those two. I'm going to find the slope of that little secant line. Well, that's going to be a heck of a lot better approximation of the slope of this line than this was, right? Or this one. And so the idea is we keep, you notice, here was the original interval, and then we made it a little bit smaller by sort of moving that point here, and then we made it a little bit smaller by moving it a little bit closer, a little bit smaller, and a little bit smaller. And the idea is we eventually want to get the width, this width, h, of this interval to 0. So in other words, I need a point really, really, really close to this point A, and this is this right here is my distance h. This is my a plus h right here, right? And I draw this little tiny secant line and I compute the slope. And that slope's going to pretty much superimpose over the slope of the tangent line, and that's how we find it. And by reducing the size of the interval to 0, what we're doing is a limiting process. And so what's going to happen is, as those 2 points get closer and closer and closer, the slope of the tangent line is going to equal, or the slope of the secant line is going to be approximately equal to the slope of the tangent line. Even though I can't find the slope of a tangent line because a tangent line only has 1 point. So, in this case here, where I'm actually trying to find instantaneous velocity, what I'm doing is I'm taking the limit as the width of the interval tends to 0 or approaches 0, meaning there's practically no width in the interval. It's this teeny, 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 tiny little distance of the difference quotient. So let me go again. Just above, the slope of the secant line is f of a plus h minus f of a over h, which is change in y and change in x. There's no limit or anything there. Okay? This is just, again, this is, you can think of this as y2 minus y1 over x2 minus x1. Okay? Down here, it's the same thing. And by the way, this is called the difference quotient. Really important. Difference quotient. Down here, it's the same difference quotient. The only difference between average velocity and instantaneous velocity is this little limit notation here in front of it. And what this means is we're collapsing the interval width to 0, or very, very close to 0, so that those 2 points are practically on top of each other. And we're finding the slope of this really, really tiny little secant line. And because it's so small and the points are so close, the slope of that little tiny secant line is going to be identical to the slope of what that tangent line would be. That's the difference between instantaneous and average velocity. So let's look at it note-wise. Let me get my paper here. Once again, average velocity we can also think as average rate of change, AROC. Okay? Ooh, why is it doing that? Hang on. My focus is going a little bit crazy here. That's equal to change in y over the change in x, which is equal to the function evaluated at a plus h minus f of a all over h. Okay? The instantaneous velocity, or instantaneous rate of change of a function. Okay, I don't know what's going on with my Elmo here, but I'm sorry about that. This is equal to, and by the way, this is called the difference quotient. Difference quotient. This is equal to the limit as the interval width approaches 0, or gets really, really close to 0, of the difference quotient. F of a plus h minus f of a all over h. Okay? This is equal to the first derivative of the function f at some point where x is equal to a. It's the slope, by the way, this is also equal to the slope of a secant line. This is equal to the slope of a tangent line. So, this is the derivative function, the rate of change, and if we're evaluating the derivative of a function at some point, then what's going to happen is it's going to be the same as the slope of the tangent line to the graph at that point. You're going to get a number, like 5 or 3 or -2, whatever it happens to be. Okay? This is just choosing 2 points on an interval on some graph that you see, any graph, connecting them with a line, figuring out what the coordinates are, and doing f of b minus f of a over b minus a. It's the same exact thing. Okay? So, these are two big concepts that may be a little abstract. So let's look at one more graph and then I'll go over some of the homework that I had posted on the board. The other thing I want you to know about graphs, and the other thing too, is that I'm going to apologize right now for the lighting. Normally I have my bright lights on when I make videos, but I was kind of lazy today, so I didn't want to pull the lights out. But I will in the future, because it takes like a whole production to make one of these videos. On page 86 of the book, there's a graph here, and there's just some things I want you to know. So it's just some function f. Distance is always the vertical axis, time. So we're looking at distance time graphs. And what I want you to notice is a few things. This function, you see there's some tangent lines that George Best, the author, already drew on there. But at any point on this graph, I can draw little tangent lines anywhere I want to, okay? And they're not coming out that good here, but anyway, there's maybe another one and another one up here. And the idea is that if this is a trip, a car trip, at the point 0, 0, I'm sort of still sitting in the driveway. I haven't driven anywhere. Maybe I'm in the garage, whatever. And then I start to drive. And if I look at the slopes of the tangent line, so here it's flat, it's 0, meaning that the object's at rest. Here it's a little steeper, here it's a little steeper. Here is probably the steepest point. And then it starts to become a little less steep, and then it flattens back out to 0, meaning that maybe we're at a red light or something. And then the steepness of the little tangent line starts to increase as we drive off again. So the idea is this. Every single point, and there are infinitely many on this curve, has maybe a different little slope if I could draw a tangent line to every single point. It's kind of hard. But I go from 0 to a positive slope to a steeper positive slope. That means that the object, or the car in this case, is increasing speed. Okay? And this is concave up, meaning concave up functions, if you think of a parabola opening up from the origin, we call that concave up, or a smiling function. Whenever a graph is concave up, when you draw little tangent lines to the curve at different points, it's going to start off from 0 or maybe negative if this were to go more this way. And then what's going to happen is the slopes of those little tangent lines are going to become more positive and steeper. The fastest point that this car is driving is right about here, because this is the steepest tangent line slope I can draw. Over here we're starting to slow down a little bit. Over here maybe we stopped at a red light or went to lunch, that we're at rest at this point. And by the way, this little region here, this is like a concave down or a frowning function. So think of an upside down parabola. Okay? It's frowning. And if I draw little tangent lines along it, it's positive, positive, 0, and then the tangent lines become negative. Okay? So in this little region here, because it's concave down, it says we're slowing down. We finally come to a stop, and then the slopes of our tangent lines become positive and more steep again. So that means we're driving off to our destination. The other thing I said in class that you should know is that speed is equal to the absolute value of velocity. And we'll talk more about this later on, but I just like to throw that in there so the seed is planted for when we do talk about that. All right, let's look at number 5. That was the first homework problem. I have to erase. And I went over this with the class. So on page 87, this is problem number 5. And we've got a distance time graph here. And it says find the average velocity for the entire trip. Well, that's easy. All I have to do is connect the endpoints of this graph with a secant line, here and here. This is the point 0, 0. This is the point 2, 100. And I need to find the slope of that line, right? So the slope of that secant line, or the average velocity then, is equal to 100 minus 0 over 2 minus 0, or 50 miles an hour. So I can say that the average velocity for the whole length of that trip was about 50 miles an hour. Then in part B it says find the average velocity of the car in the second half of the trip. Well, the second half of the trip, if this is 2 hours, goes from time is equal to 1. So that's 160. That's the point 160 right there, to the end of the trip, which is 2, 100. And I do the same exact thing. I connect them with a secant line, or a line called a secant line, and now I can just say that the average velocity is 100 minus 60 over 2 minus 1, or 40 miles an hour. Is that okay? Next question, is the car slowing down or speeding up during the first half hour of the trip? Well, this is 0 and this is 1 hour, so these are measured in quarter hours. So here's a quarter, so here's the first half hour of the trip, from 0 up to this line right here. What I know is if I draw a tangent line here, it's flat, it's 0, it has a slope of 0. And then the tangent line starts increasing. I also notice that around here it's kind of concave up, so I would expect that the car is speeding up over that interval. Then we're asked to estimate. So sorry about this, but usually I print graphs out, but I was kind of busy tonight, so I'm just using the book. D is estimate the instantaneous velocity at t equals to 1 and t equals to 1.5. So here's t equals to 1. Now they're saying instantaneous. The I word is there. So what they're talking about is the slope of the tangent line to this curve at the point where x is, or t is equal to 1. X is equal to 1, t is equal to 1. So 1 is my a, okay, when x equals a. So, you know, again, I really can't estimate a line with only one point on it. But what I do know is that, you know, we found the average velocity over the second half of the trip, which was 40 miles an hour. I could find the velocity over the first half of the trip, which is 60 miles an hour. And I could add those two up and divide by 2, and that would give me a pretty good approximation. Would it be the best approximation? Probably not. But it would be a pretty good one. Okay? So I could say, you know, around 50 miles an hour. And I'd be okay. What about at t equals to 1.5? So here's 1.5 hours. If I draw a little tangent line to that point, I'm at rest. So my instantaneous velocity is 0. Okay, whenever an object's at rest, velocity is 0. So I don't even have to do any work. I don't even have to show that. I mean, it's a flat spot in the graph. It's going to have a horizontal tangent line. The slope of a horizontal line, period, whether it's tangent or not, is 0. Then the most interesting part of this question says, estimate when the instantaneous velocity of the car was the same as the average velocity for the entire trip. Well, the average velocity for the entire trip was 50 miles an hour. We drew a secant line from endpoint to endpoint, and we computed that. Right? What this means is, so what this question E is asking is, when is the slope of the secant line equal to the slope of the tangent line? When is the average velocity equal to the instantaneous velocity? Well, two slopes are equal if their lines are parallel, right? Parallel lines have equal slopes. So what I'm looking for are places on this graph where I could draw a little tangent line such that it would be parallel to the secant line. So maybe right around here, maybe right around here at t equals to 1, and maybe right around here. So again, I could be off a little bit if you check with Bob, the back of the book. And the answers for this, you know, he's probably got a more precise one, and Bess does this a lot because he knows what this function is. He put it into his program. He, you know, dragged and dropped it into the document called the page of this book, and he knows what the function is. He's just giving you the visual of it. So a lot of times when you look at Bob, it'll have, like, you know, when t is 1.593 hours or something, and it's like, okay, I could have never gotten that from looking here, but we can safely say at about t equals maybe about 40 minutes, maybe at about 1 hour, and maybe at about 1 3/4 hours. This is parallel to the secant, this is parallel to the secant, and this is roughly parallel to the secant. Okay, so at some point along this whole trip, your average velocity equaled, for even just 1 split second, your instantaneous velocity. And on this graph, it happens 3 times. Here's another homework problem, number 7, where you've got a distance time graph, and you have to answer the questions. So there's some points labeled on this graph, A through D, and part A says, at which point is the car traveling the fastest? Well, you want to look at whatever point has the steepest little tangent line slope. You can draw a tangent line here, one here, one here, and one there. Now, this kind of doesn't count in a way because you can't go past that point. The interval does not continue on. So keep that in mind, that while it may look that way, this cannot be the steepest part. The steepest part is in the middle here, right here, and that's where your car is going to be traveling the fastest, at point B. At which labeled point is the car stopped? Wherever you see a flat spot, that would be point C. Okay, so at point C, the car is stopped. Find the average velocity between time equals to 1 and time equals to 4. So what are they asking for? The slope of the secant line between t equals 1 and t equals 4. So we're looking at this secant line here. This is 490, and this is 120. So this point here is 120, and this point has coordinates 490. So I could say m secant, or average velocity, however you want to write it, is equal to 90 minus 20 over 4 minus 1. That's 70/3. Leave it like that, miles per hour. Estimate the car's speed at point A. Not between 2 points, but at point A. Estimate it. Oh, geez. Tangent line problem, right? Well, you know, I could find the slope of the secant line from 0 to A, and then from A to 2, and take the average if I want to. But I'm going to do the lazy thing that we can do with the graph. And I'm going to get my little straight edge here. And this is what I'm going to do. So whenever you have a graph, you can do this. I know that that point's 120. I'm focused on this point A. What you do is, you know this point is 120. You put your ruler on there like a tangent line, and you find some other very convenient spot in the grid where you can draw this. So maybe like this one right here. well, that's a bad line, but so this line is tangent to that point, and it has the point 120 here, and it conveniently goes through this intersection of the grid at 250. I can use those two numbers, right? I have this point right here, and I have that point. I found 2 points on that line, so I can use the slope of a secant line, 50 minus 20 over 2 minus 1, or 30 miles an hour at that instant. At point D, that's a little bit different because, you know, I can't extend this way. There's no more graph, okay? So endpoints are special. But what I can do is maybe draw a tangent from this point to some other convenient point in the grid. You see what I'm doing? I'm manipulating. Oh, that's bad. Let me change, let me fix it, hang on. And this is legit, by the way. So like, that's tangent up to that point, pretty much. So I have this point 490, and I've got this nice convenient little intersection in a point at the intersection of a grid at 370. And guess what? I can approximate this tangent line by 90 minus 70 over 4 minus 3, or about 20 miles an hour. If you get confused by any of these, most of you have, what do you call it, calculus honors, so we can go over it again in class. Here's another graph, number 8. This is not part of the homework, but I did bring it up in class. Label T sub 1, T sub 2, T sub 3, distance time graph again. When is the car moving the fastest? I draw some little tangent lines at those points. Wherever I have the steepest tangent line, be here, right at T sub 2. When is the car speeding up or slowing down? The car is speeding up from about 0 to T sub 2, concave up, speeding up. And then, if you notice here, here's a slope of, let's say, 1 for this tangent line. This is a little less steep. This is a little less steep. You see what's happening to the tangent lines? So we're slowing down from T sub 2 to T sub 3 because concave down, slowing down. Is the car speeding up or slowing down between T sub 2 and T sub 3? Well, it's slowing down. Okay? It's only speeding up in the interval T sub 1 to T sub 2. It's actually speeding up there. Okay? Another way you're going to see it is through tables. AP Calculus loves graphs and they love tables. So, here's a table where a ball is dropped from a building. Now remember, you're always dealing with distance time. Time is on the x-axis and distance is the y-axis. Okay? So don't let this confuse you. Just think of these values t as x's and these as y's. Okay? X, y. And the time interval goes from 0 to 5, and these are the output values. When I plug a 0 in, I get a 0 out. When I plug a 1 into this function, I get 15.07 out. So these are the input values, or the independent variables, and these are the output values of the function. Okay? So it says, plot the points, label the axes, blah, blah, blah. Well, I'm not going to plot those points, and I don't expect you to either. What I know is that this function is increasing, right? It starts from 0, goes to 15, 57, 127, 200. So it kind of looks, you know, something like that, if I plotted those points. And it says the slope of any secant line is a measure of velocity. Why? Sorry, the slope of any secant line on the graph is a measure of velocity. Why? So I want you to think about that one, because I didn't answer that in class either. Not because I didn't want to or couldn't, but because I want you to think about that a little bit. Okay, make an estimate of velocity from T1 to T2. Well, look, forget about the graph part. from T1 to T2, that's this interval here. If I have to estimate velocity, the best I can do is 57.9 minus 15.07 divided by 2 minus 1. The change in y over the change in x, and that's my estimate of instantaneous velocity. From 2 to 3, I would do the same thing. It's a completely different interval. This is the interval here. 127.03 minus 57.9 over 3 minus 2, and I would get a number, right? And that would be the best way I could estimate the velocity over that part. But from 1 to 3, now I've got an entirely new interval. And not only do I have a new interval, here's the interval from 1 to 3, but this thing right here, which was a minute ago a rightmost endpoint, and then in the second part of the question was a leftmost endpoint, right? This is an endpoint of an interval, that's an endpoint of that interval. Now it's in the middle of the endpoints of my interval. It's easy. You could do this first and get the number, and then that and get the number, and then divide by 2, add them up and divide by 2, take the average, and that's going to give you a really good estimate of instantaneous velocity when t is equal to 2 at this point. Why? Because this point, 2, is in the middle. But another easy way to do it, since we have a very small interval, I could just do 127.03 minus 15.07 divided by 3 minus 1, only because this is in the middle and I'm going to get the same exact answer, or pretty much the same exact answer. Okay, so what I want you guys to do is to try number 13, which is the last homework problem from this section. Find her average speed over the whole swim. You should be able to do that very easily. And then estimate her velocity right here at 14.6. Remember, this is x, this is y. Choose something on the left, something on the right, and try to approximate the instantaneous velocity, and you can check with Bob, the back of the book. That's all I'm going to cover for now, because I am going to go over this again, because with some classes I got really excited and I went off on a tangent. No pun intended. I'm also kind of losing my voice because I had a very quiet summer and now I'm constantly talking and I feel like I've got something scratchy in my throat. So anyway, I'm going to give you a rest and give myself a rest. So anyway, think about those things. They're not that hard, but they're different than what you're probably used to. And I'm going to go over it again on Monday, and I'll go over any questions you have in Calc Honors tomorrow during 4th block. I know you have a pep rally, but I will answer questions until the pep rally. So anyway, mull over this, and I'll answer any questions that you have when I see you again. All right? Have a great weekend.